All right, so we're revisiting this question about nitrous acid and how the H plus ion concentration and pH is dependent on what else is in solution. So we did it first on its own, then we looked at its percent ionization, and then we did it much more dilute, so we had to use the quadratic solution, and we found that dilute solutions give higher percent ionizations. And now we are looking at it with an ionic contaminant. That contaminant, this is a weak acid, so it only ionizes a little bit. This ionizes completely. It puts sodium and chloride into solution, which gives us an ionic strength if we were to go through that calculation again, which is this number. Because it's 1-to-1 salt, it is half of the concentration of the charge of the first, of the cation, plus half of the concentration of the charge of the anion. So this ends up being the same number. That then sends us into a table to find these values for the activity coefficients. Activity coefficients for ions have numbers, but intact molecules don't. And then the Ka is from our original textbook value of Ka that we used all the way back at the original value. And our modified value for Ka is the one that's based on activities. Okay, so this was the Ka that came from the concentration. And if we say that the real number with activities, the activity is the concentration multiplied by the modifier right here, which is the activity coefficient, then we could just jumble all these together. And that gave us a value, a new value of Ka of 8.16 times 10 to the negative 4. Okay, having done all of that work, let's now go ahead and find the equilibrium concentration of H plus. And nothing has changed here. A change and an equilibrium, that my initial concentration is 0.15. There is none of this, none of that. I'm going to lose some of this, make some of that, make some of that. These have to be equal numbers because they're equal to each other stoichiometrically. So at equilibrium, I have this and this. My value for Ka is products divided by reactants, is H plus NO2 minus over H plus, which gives us x squared, x and x, divided by 0.15 minus x. Okay, now we have a table. For those watching along at home, this table tells us when and when not we can use the approximation that this value doesn't matter. Tell me if I can use it or not. That table tells us that if we use that approximation, it's going to introduce a percentage error of about this value. K is now 8.16 times 10 to the negative 4.
We would have somewhere between
So the way that we do it is we put the concentration over the Ka. For us, that is 0.15 divided by 8.16 times 10 to the negative 4. That gives me a number.
I got 183.
183. Okay. And so then we look in this table. It's not the best table in the world because I don't particularly like the scientific notation at the end right here, but it works. 100, no, no. The scientific notation is where? Oh, it's in the middle.
Yeah.
Right. It's showing people at home the wrong thing. This, right here. So I'm going to look for about 200 because my actual number is 183. Going to look for about 200 on that list. And it appears right here. So it's a 5% error. Question. Are you gonna, this introduces about 5% error into your equation if you use that approximation. And the question is that 5% worth your time doing the quadratic?
Depends on what.
It's up to you. Your number's off at 5%. We have two significant figures in the question. Where does 5% show up as?
The 100,000.
So I only have two significant figures anywhere in my number. If my number is three significant figures, now it is. 5% is there. At 10%, it's there. If my number's 4%, it's not going to impact my answer at all. At 5, it might plus or minus that digit. Gonna let it slide.
Okay.
I have two significant figures.
Okay.
Two. Am I working with really precise numbers? With two significant figures?
No.
No. No. Okay, so I'm going to let this stand, and it will be now equal to 8.16 times 10 to the negative 4. All right, x is representative of h plus, and it is equal to the square root, because x squared is this number multiplied by that number. You'll be doing this in your sleep soon. There you go. X is this number.
I got 0.011.
Mm-hmm. Polita. Well, Polita. Okay. We're going to do a pH on that? Have we've been doing pH the whole way through?
Yeah, and originally, the original question asked for pH.
So pH is the negative log of 0.011.
I got 1.96.
That sounds about right. I don't actually have my number down here, but that sounds about right. Okay, in the other questions, in fact, I don't have pH in any of my answers. I've been tagging it on as we go. But I'll, if I need to know, I can watch the film back, because we have it now. All right. Here's a follow-on question. We're going to need a couple of numbers. We're going to need to pull numbers from the different parts of the question so far? We were told in general chemistry that sodium ions and chloride ions in this kind of scenario are spectator ions. Were they? Question. Answer. No. Question. How much impact did they have? So what we need is the previous number for H plus concentration and the new number for H plus concentration. And we're going to look at the difference. So from, I didn't really number these parts 1, 2, and 3, did I? I didn't give them numbers. But from the very first, so the initial question, the H plus from H and NO2 was equal to, find that number, that was our very first calculation. Yeah. I have it down as a 2. Okay. When we added sodium chloride, this is the number. Nope. Yes. I thought for a second I got the number of zeros wrong. Okay. Comment on the size of those numbers.
They're small, but
They're both small.
But they're both they're both near each other, but it's obvious that there's a difference. Like
Which one's bigger?
the new one.
I do like to write my numbers. I don't know if they still do this in primary school, but
We used to make the numbers line up so that we could do units and tenths and whatever. This is bigger. Is it supposed to be bigger?
Well, if we assume that there would be no change, it would be the same, not bigger.
Yeah. Yeah,
But
is the number supposed to be bigger? We found that number. I mean, if that number was wrong, maybe I just let it be wrong, and we would get to this part where you use your brain. There are numbers on the board. They're different from each other. Are they different from each other in the correct way? Which of those two numbers is supposed to be the biggest number? No,
No?
because
The NaCl has the.
ionic strength. In lab this morning for organic chemistry, they made ester. Have you noticed the lovely banana smell in the building? Head that way. We had stuff in the separatory funnel, and there's an organic layer on the top where our delightful banana ester was, and then an aqueous layer. And they shook it a couple of times. They shook it with water. They shook it with sodium hydrogen carbonate because this was performed in acid. So just to make sure that we neutralize everything in there and have our product be neutral. And then instead of shaking with water, they shook with saturated sodium chloride solution. I went to the stock room, I got the bottle of salt, I poured salt into some water and stirred it for a bit, shook it for a bit until there was a precipitate, saturated. What's the whole point there? If there's anything ionic stuck in the organic layer, and it was reluctant to go into the aqueous layer, now it can't resist. Because I just increased the what?
The ionic strength.
The ionic strength of the solution. With water, water's really ionic, but salt water is more ionic than water. And so now any impurity that was in that layer now gets pulled into this layer where the very high ionic environment is. So, when this acid is reluctant to put its H plus into water, make it be salt water, and it will put its H plus into salt water better. How much better?
Is it the bigger number minus the small number all over the bigger number times 100?
You can do it any way you want to, as long as you frame it with reference to which way you have used the numbers. Okay, this number is better than that number. So if you use, if you frame it that way, you would say you get a percentage, and you would say it was a percentage increase.
Yes.
And if you framed it the other way, you would say it would be a percentage decrease. So, don't mind. The difference is the same,
Yeah.
just the way that you frame it. So if you do little number minus big number, the difference is going to be negative. If you do big number minus little number, then the difference is going to be positive. So I would do big number minus little number. There might be some mathematician out there screaming, no, 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 there's a strict way. But I think that if you know what the numbers mean and you frame it with the reagents in mind, then you're okay. And then divide this by what? The big number.
Yeah, I got 16%.
And then multiply that by 100. I think that number's somewhere like 16 or 17%. Was it 16 point something?
16.36.
Okay. That's a 16% shift in acidity. Just because of the medium that you've put the acid in. the medium being either the acid is dissolved in pure water or the acid is dissolved in salt water. Okay? Okay. Do I have another question? Yes, I do. Yeah. Okay. All right. Let's do it again, but we're going to change the impurity. So technically, what's coming up now is part 4. Part 1 was just HNO2, and it was at 0.15 moles per liter. And we used the approximation. And then 2, we diluted it. Did we dilute it by 10 or what? I can't remember.
It would change the molarity to 0.0015.
So we diluted it by 100. Okay. And at this solution, you needed the quadratic, because now if we went and looked at that table of HA over K, that's gonna give us a big error. And then 3 was back to the original concentration, and we did it with sodium chloride. It's 4. I'm going to use the same concentration. What is the H plus concentration of 0.15 molar nitrous acid with 0.05 molar sodium, what? NaNO2. Yeah. So this is nitrous acid, nitric acid being a strong acid, and this is sodium nitrite, not nitrate. It's NO2 minus. Okay. There are 2 ways to do this. The long way and the convenient short way.
Let's do the short way.
I have 2 things in solution then. It's useful to draw them on top of each other, because when you stack them on top of each other, alarm bells go off, because
There's a
common ion. And there's a whole half chapter in the General Chemistry 2 textbook that says, hold on a minute, you've introduced something into solution that is part of my equilibrium. And so Le Chatelier is going to say, yeah. Le Chatelier says, you now have too many products, push back to making a reactant. Okay. Which is a good place to start the conversation. It's not 100% exactly that way, but it's good. So what we could do is we could go find the concentrations of those 2 in equilibrium. They will be the same as each other, but this one's added. This one has something added to it, and you can just work out the equilibrium and go. But somebody else has already done all that work for you. is Henderson and Hasselbalch. Remember these two guys?
Yeah.
And they said that the pH is equal to the pKa plus the log of the A minus divided by the HA. This is for any generic weak acid, HA, weak acid equilibrium. Okay. This assumes a couple of things. For us, so this is the generic form. For us, this is nitrite, and that is nitrous acid. We're going to make two assumptions. First of all, I'm going to assume that all the anion comes from the strong electrolyte. There are two things putting nitrite into solution. One of them is from a very small weak acid equilibrium, and the other one is from a strong electrolyte. So we know that this one goes 100%, and this one has a Ka of 5.9.
5.62.
Times 10 to the 4. Okay. So, in comparison, which one of these two is generating all the nitrite? This generates some, but not nearly as much as that. So that could be many, many decimals down the line. I'm going to assume it all comes from here. And then I'm going to assume that the HA minus X is equal to HA, saying that the Ka is small and that this is essentially undissociated. Okay? So I'm not even going to bother finding the equilibrium concentration of that.
Great.
I'm just going to say, you know, it probably didn't change very much. And that will be true as long as Ka is relatively small. If Ka is not a relatively small number, then no. Okay. This, we've got three things. There are three possibilities. So pH equals pKa plus this term. Let's look at this term on its own. There are three possibilities. That the log of A minus over HA that's the big number. If that number is bigger than that number, we need to look at that scenario. There is 2, and then there is 3. And in the third scenario, we need to look at what happens when that number's the big number. Look at the wording in our question number 4. What is the H plus ion concentration of 0.15 molar nitrous acid in the presence of 0.05 molar sodium nitrite. Are we 1 or 2? Are we this description or that description?
One. No. Because there's 1.5 molar of HNO2 and 1.05.
For us, specifically in this question, it would be the log of nitrite divided by, that's an H, nitrous acid. Here, the log of nitrite concentration. Oh, that's too much. Divided by the undissociated free acid. Okay, in our question, is that number bigger than that number? Or is this number bigger than that number? Are we a 1 or a 3?
3.
What's the value for NO2 minus?
0.05.
Assume all of this comes from the sodium salt. So we're just going to use the concentration of the salt. What this tells us just pull that concentration straight from the question. And this one tells us just go ahead and use the, I almost wrote HNO2. I want to still be generic. Just use the undissociated from the question. Okay, so for us, we've got this, with case number 3, that it is log of 0.05 divided by 0.15. Okay. 0.05 divided by 0.15 gives me a number that is less than 1. Less than 1. And when you take the log of it,
Make it negative.
this is going to be a negative number. This term is negative when the denominator is larger than the numerator. When the numerator is larger than the denominator, that term goes positive. So this top case happens, positive values, when A minus is larger than HA. Here, this bottom one happens when A minus is less than HA. And we have a middle case. Guess what the middle case is?
When A minus is equal to HA.
Mm-hmm. When A minus is equal to HA, think of a number, any number, divided by itself.
You get 1.
You get 1, and what is the log of 1?
0.
So when these two values are the same as each other, this whole term goes away, and pH is equal to pKa. Okay. This is just a little aside so that we know where we are. When our number turns out to be negative, that we know what that means. And when it turns out to be positive, the next question down in the homework, hold on a minute, it was positive, it was negative a minute ago. Yes, it's going to change. Okay, let's put our numbers in. Those are our 3 scenarios. pH equals pKa plus the log of A minus over HA. What's a pKa?
It's negative log of K.
P function can be applied to anything. Anything at all. Okay. So pH is equal to the negative log of 5.62 times 10 to the negative 4. That's our Ka for the nitrous acid, weak acid dissociation constant. And then I'm going to add to that the log of the source of all of the nitrite in solution. We're going to assume it comes from the ionic salt, not from the equilibrium. And then we'll divide that by the concentration of the undissociated acid. We're going to assume that none of the acid dissociated, or a negligible amount did. And let's break this into 2 parts. What is the pKa? Oh, did you do it?
Yes.
What is that?
I got 3.25.
Yeah. Okay, so Ka is a number that is less than 1. If you take the log of it, it's going to be a negative number. But the P factor has a negative built in, which turns our negative numbers into a positive number. So this is a positive number. And then I'm going to add to it the log of this quotient, where it is bottom heavy. So this will be a negative number. So I'm going to add to it negative 0.477. That's the pH. pH equals what now? 2.8 something. 2.77. Is that right? Okay. That's pH. We've always found pH by finding H plus first. Now we're being asked to do it the other way. pH represents the negative log of the H plus concentration. So H plus, find the log button on your calculator and do the inverse of it. This is 10 raised to the negative value of the pH, which is 2.77. What'd you get?
I got 0.0017.
Oh, yeah, okay. I got that as 1.7 times 10 to the negative 3. Can you make, you've got to go, did you find another way of getting to the log without doing?
I just found it. I have to look it up.
Yeah. I can't think what they
whatever is the opposite of log.
So, yeah, I know,
It's
so
in
it's,
the
it's
Cause you just second, yeah.
so printed on here that wherever you find the log button, there. So the opposite function is 10 to the x, and we're doing negative log, so our opposite function is 10 to the negative x. Yeah, you might be working a little bit harder than everyone else. Because, yeah.
Okay, all right. What if, instead of that being a weak acid, it was a weak base?
Oh, wait, are you gonna do like KBs or KAs?
Yes. The thing is, when you go and you look these things up, you go looking for a table. Now that the internet exists, there are such things out there as KB tables. But that's not what most of us are looking for. I think it's Appendix G in our book. Here are our acid dissociation constants. There's a whole appendix for them with lots and lots and lots. I think I don't know how many pages long it is. Many, many, many pages long. And they're all KAs. Okay. Now, if you are a base, you do basic things. It's just the opposite of being an acid. But the number associated with you in the table is an acidity constant. It's an acid dissociation constant. But the base says, but I'm not an acid. So you have to think about it in reverse. We're not interested in strong bases because strong bases put all of their ions into solution and then generate OH minus, which then pulls H plus out of solution. So the act of being a base removes H plus from solution. That's what bases do. Bases make bonds. What are our three definitions of acidity or basicity? So they have names. Arrhenius, Lowry and Bronsted, Lord Gilbert, Lewis. What's an Arrhenius acid?
Is it the one that deals with H plus?
Yes.
Okay, then it removes or decreases concentration of H plus?
An acid?
No, oh, the acid.
So I
increases.
asked acid first.
Oh, sorry. It increases the.
An Arrhenius acid is anything that increases H plus concentration. So an Arrhenius base is anything that decreases H plus concentration. What is a Bronsted acid? It's a proton donor. Because an H plus has one proton, no neutrons, no electrons. H plus is a proton.
So,
So a Bronsted base,
is it proton acceptor?
proton acceptor. And then Lewis says that an acid is
Gives away, or as it accepts electrons.
an electron pair acceptor. And so a base is an electron pair donor. And in those disciplines like organic chemistry, when you see the base will have a lone pair of electrons, and it's the thing reaching out and grabbing hold of the acid. Okay. NH3 is a weak base. It has an equilibrium in water that looks like this. Think about those definitions. I'm going to reduce the H plus concentration that is in solution. I'm going to accept proton, an H plus, and I'm going to donate a pair of electrons. So the pair of electrons on that nitrogen reaches out and grabs one of those hydrogens. And your ammonia becomes ammonium. What's left? Yeah. And that hydroxide will then go on and remove H plus from the solution. Okay. That's in equilibrium, and I would like to find the value for this equilibrium constant right here. It's in the book. It's in Appendix G. That K is written currently in the direction of being a base. So this is a K, but it's a KB. The reverse, where my NH4 plus interacts with the base, an actual base, a strong base, and makes NH3 and H2O, that would be written as a Ka. Because from here to here, I'm losing H plus. That's the very definition of being an acid. And from here to here, I'm gaining H plus. Okay? So when I want to find the value of K for this particular reaction, I have to have a little bit of chemical knowledge, because when I go looking in the table, I cannot find this, because everything in my table is written as an acid dissociation constant. So I have to know to think backwards. Okay. If this is the base, What name did we give to that?
Conjugate acid.
This is the conjugate acid. So I'm going to look in the Ka table for the conjugate acid. All right. It's Appendix G.
Ka of ammonia is 5.69 times 10 to the negative 10.
Ka is 5.69 times 10 to the negative 10. Okay. Let's pretend for a second that you didn't have a Ka table. What if you only had a pKa table? Tell me it's pKa.
9.245.
All right. If the only thing that you could find was the pKa for ammonium, you would then convert that into the Ka. Okay? The pKa is negative log of the Ka. Therefore, Ka is 10 to the negative, whatever the Ka is, and for us that is 10 to the negative 9.245, which equals 5.69 times 10 to the negative 10. Okay, so just in case you can't find a Ka table, but you can find a pKa table, you can turn Kas into pKas. Okay. Water is in equilibrium with its acidic form and its basic form. Kw is equal to the concentration of the H plus multiplied by the OH minus. Kw is equal to Ka multiplied by Kb. And at 25 degrees Celsius, Kw is 1.0 times 10 to the negative 14. We have seen that that number can shift with temperature. Okay. Go ahead, find the value of Kb. Kw equals Ka multiplied by Kb. Therefore, Kb is equal to something. Just gotta rearrange this, put the numbers in. KW plus KA multiplied by KB. That means that KB is KW divided by KA, which is 1.0 times 10 to the negative 14 divided by 5.69 times 10 to the negative 10. Looks like I'm going to have a number that's somewhere around negative 10 to the negative 4.
I want 1.76 times 10 to the negative 5.
0.0002.
We need to look at your calculator and make sure that you're doing the right thing. Alright, this is on par with the KAs that we've seen for weak acids. Our weak acids typically have been 10 to the negative 4, 10 to the negative 5. So that tells us that ammonia is about as weak a base as most of our weak acids are. Okay. We'll go hunting for an equilibrium concentration on Thursday. And it's exactly what it sounds like. And then